In this section B type of question, so we have this series of statements. It is my understanding, and it is hopefully your understanding as well, that these section B type of questions have been phased out in the 2022 syllabus onwards for the multiple choice paper. However, just because they phase it out does not mean they cannot ask you. It's just that there wouldn't be a fixed 10 questions. They could ask you 5 questions. They could ask you 11 questions. That means there's no particular section B. It could be anywhere throughout the whole paper, without a specific section for these type of questions anymore. Question 31. So we check statement number 2 first. We have this isotope technetium. If we have a look in the periodic table, technetium is just underneath manganese. So there is 99 technetium. Sorry, technetium 99, that's how you pronounce it. The proton number of which is 43. So what we have is the number of protons is 43, because that read as protons or atomic number. These are the smaller number at the bottom of this kind of nuclide notation, the international standard here. This is the nucleon number, or what you call the mass number. That basically tells you how many protons and also how many neutrons you have in the nucleus of an atom. So to work out the neutrons, you just minus the proton number from the nucleon number. So what we get is 99 minus 43. I get 56 neutrons. In terms of the electrons, what I have is an atom. So the number of electrons must be equal to number of protons, because I have atom, which overall is uncharged, electrically neutral, because the charges from the 43 electrons must balance out the positive charge from the 43 protons. So what statements about these are correct? So it has 43 proton. That's correct. The proton number is 43. 13 more neutrons than protons. So 56 minus 43. So 56 minus 43, I get 13 extra neutrons than the protons, than the number of protons. Now it has 99 nucleons. It has 99 as the nucleon, the mass number. So 99 nucleon is entirely correct. So all 3 statements are correct. That's option A there. Urea is a product of animal metabolism, so it can be used as a fertilizer. As you know, urea in your urine typically are good fertilizer, obviously. Smells like ammonia. They can get broken down and be used as a fertilizer, obviously. Now this diagram shows angle X in this molecule. To work out the angle there, you need to know the shape. To know the shape, we have to look at this carbon here. Around the carbon, how many bond pairs are there? How many lone pairs are there? This is a double bond. In a double bond, what you have is maximum of 1 sigma bond, which means the remaining 1 covalent bond must be a pi bond. We know sigma bond is formed by orbitals overlapping head-on, and the pi bond is formed by orbitals overlapping side-on. So if we look at statement number 2, the molecule has 2 pi bonds, 2 pi bond. That's definitely wrong. The rest of these are single bond. They're all sigma. This is the double bond. There's 1 sigma and 1 pi. So that means we only have 1 pi total in the whole molecule. So 2 is wrong. I already got my answer, which must be option 1 only is correct. But I'm just going to show you why option 1 is correct. Around the carbon, we have 1 sigma there. We have another sigma. We have another sigma. So altogether around the carbon, we have 3 sigma bond. This means there are 3 bond pair of electrons. In terms of lone pairs, this carbon form 1, 2, 3, and 4 covalent bonds. There's 0 lone pair left on the carbon. Without any lone pair, in the absence of any lone pair, the 3 bond pair repel equally. So what you get is you get a trigonal planar geometry, and this trigonal planar geometry has this bond angle 120 degree. Trigonal planar geometry, carbon sp2 hybridized, because 3 plus 0 give you 3 electron pairs, and from there you can get 1 of the s orbital. 1 plus 2 give you 3. Therefore, 3 electron pairs, 3 of these hybrid orbitals. 1 of the p orbitals on the carbon is unhybridized, and they can overlap sidewise with the p orbital on the oxygen, and they give you the pi bonds formed by orbitals overlapping sidewise there. In terms of statement number 3 being wrong, even though we can move on because we already established that 2 was definitely wrong already, but I'm doing a tutorial, so my point is to show you why option 3 is also incorrect. So 3 lone pairs of electron is wrong because it is only the oxygen. The oxygen has 2 lone pair remaining. The nitrogen has 1 lone pair remaining. So altogether you get not 3 but 4 lone pair of electrons, 2 on the oxygen, 1 on each of the nitrogen there. Now the next question, aluminum is extracted from aluminum oxide by electrolysis. This is a common O-level, IGCSE level, it was GCSE level chemistry, but it was 14 to 16 years old chemistry, and this topic on electrolysis has been phased out from the AS chemistry, as far as I know, from the Cambridge new syllabus for 2022. But they are still within the syllabus for the A2 bit, where they like to ask you calculations and stuff. Anyway, let's just do it. Bauxite is added to help to lower its melting point. It's definitely not bauxite, it's actually cryolite, which is added to lower the melting point of the electrolyte. If 2 is wrong, only 1 must be correct. And the very reason we use cryolite in the mixture of the electrolyte is because of this very high melting point, very strong ionic bond between the small highly charged cations and the small highly charged anion, very strong ionic bond, and therefore it's something that will require a large amount of energy to break in this giant ionic lattice, very, very high melting point, and cryolite can help to lower its melting point. And as a chemical engineer, you will please your boss by saving your boss some money in the operating cost there. Question 34, why does raising the pressure of a fixed mass, so you have a fixed mass, this is a gaseous reactant, this is a constant temperature, and this can cause an increase in the rate of reaction. So your rate can depend on the pressure of gases. So this is gaseous reactants. So when we increase pressure, we are squeezing the particle closer together. So we're making the particles closer together and they can collide more frequently. So in terms of option number 2, more molecules have energy greater than the activation energy at the higher pressure. More molecules have energy. More molecules have energy. You are just raising the pressure, but you don't change the mass. If you don't change the mass, there is no change in the composition, no change in the amount or the number of reacting molecules, and therefore how can you change the area under the graph if you don't change the amount of reacting molecules? And this one is saying that if you don't change the shape of the graph and if you don't change the shift at all, because only temperature can change the Boltzmann distribution, so more molecules have energy than that is not going to be correct, because Boltzmann distribution is to do with energy distributions, and that shape can only change when temperature changes. So we're looking at collision frequency increases, but not in terms of the energy there. Okay, so only option 1 is correct there. Question 35, which statements about the industrial manufacture of sulfuric acid? So that is part of the contact process. That is what is called as one of your case study from your O-level, GCSE level, or IGCSE level days when you're doing the 14 to 16 years old simpler kind of chemistry. Now the stage that forms the sulfur trioxide also involves a V2O5 catalyst. That is definitely correct, because that is the state that is actually quite difficult to achieve as a result of you being in equilibrium. So in order to speed up the equilibrium, I said speed up the equilibrium because all it does is speeding up the reactions, increasing the rate of reactions without changing your position, without changing your equilibrium yield. It just helps to the reaction to speed up a little bit more. Okay, now the sulfur is burned to form sulfur dioxide. That is actually stage 1. We burn the yellow color sulfur solid, burned in oxygen, clean oxygen, pure oxygen, you're going to get sulfur dioxide. So that is correct there. The stage that forms sulfur trioxide is non-reversible. That is actually wrong. That is actually in equilibrium. That was the step I've just shown you for the step that require catalyst. Is in equilibrium. That is why pressure and also temperature, as well as the use of catalyst, are all very important in ensuring that the equilibrium produces a good yield of SO3 and also at a good enough rate, at a fast enough rate, such that you don't have to go to far extremes of the temperature or the pressure conditions. So that thing is wrong there. So 1 and 2, that's option B, are correct there. Question 36. So X is a group 2 metal. I think the new syllabus, they've changed the notation to being group 2 like that. It's the same idea really. It forms a sulfate which is more soluble than barium sulfate, but it forms a hydroxide which is also more soluble than calcium hydroxide. So we're going to think about the two graphs. So these are not exact value, but these are how I've always remembered the solubility of the group 2 sulfate. In terms of the group 2 sulfate, we know that the barium sulfate is an insoluble white precipitate, but magnesium sulfate is very slightly soluble in water, and therefore magnesium sulfate has a higher solubility than this barium sulfate, which you have precipitated out a lot in your entire life doing practicals, especially tests for the sulfate anion, even since you were doing simpler chemistry back then. In terms of the solubility of the group 2 hydroxide, down the group as the cations get bigger, so the barium hydroxide is way more alkaline, is way more basic. That is because the hydroxides are completely soluble in water, whereas things like magnesium hydroxide, when you try to dissolve magnesium hydroxide in water, they are not very soluble at all. Very little of it dissolve, therefore you get something like pH 9 there. So in terms of a sulfate, which is more soluble than barium sulfate, it can be any of these. So it can be magnesium, yes. So let me just think about the sulfate. More soluble than barium sulfate, yes, and yes. They are all more soluble than barium sulfate because barium sulfate is all the way down there. Now you want it to be more soluble than calcium hydroxide. So where is our calcium hydroxide? Calcium is below magnesium, so calcium is going to be more soluble than magnesium hydroxide, but you want it to be more soluble than calcium hydroxide, so I cannot have magnesium, so magnesium cannot be the answer. Beryllium would be somewhere there. Perhaps I've gone too far actually. If I just extend this a bit longer, so beryllium is above magnesium, so therefore beryllium hydroxide is less soluble than magnesium hydroxide. So this thing, more soluble than calcium hydroxide, must be any of the hydroxides of group 2, the group 2 must be below calcium. So magnesium can't be the answer, beryllium can't be the answer because it doesn't satisfy the hydroxide condition here. So 2 was wrong already, and that was why 3 must be wrong as well, leaving only 1, which is option D being the correct answer. Because in terms of the hydroxide, you can only fulfill that with, I don't know why my handwriting is terrible, you can only fulfill that with the strontium hydroxide as well as strontium sulfate for both the conditions here. Question 37, what we have is an alkene molecule. This is the double bond, the alkene there. Which statements about this molecule are correct? It has geometrical isomers. If I try and draw the skeletal formula, because it's a lot simpler to draw the skeletal formula. Let me see if I can draw this a lot better. So I've got CH3, I've got that, CH2, CH3. So this is CH3, double bond, CH3, CH, carbon from 4 bond, there's a CH there, CH3 there, a CH2, and then a CH3 at the end there. So what we can see is this group, and this is the higher priority group, as this one has a higher molecular mass than that. So these two high priority groups are on the same side. That's what we call cis there. Okay, you might not have learned that. You might be thinking that CH3 and CH3 on the opposite side, you might think it's trans, but in reality we are looking at the molecular mass of the side group in order to decide if the high priority groups, meaning the high MR group, the one with the higher priority, are they on the same side or are they on different side there. So here essentially what we have there is trans. But I mean, whether you get this as cis or trans, doesn't matter. You know that these are geometric isomers, so it is entirely possible that all the carbon atoms are in the same plane. It said all the carbon atoms are in the same plane. That means all are carbon sp2. But very clearly, we have quite a lot of carbon sp3 here. This is carbon sp3, carbon sp3, carbon sp3, carbon sp3 there, and only these carbon sp2 here are the alkene carbon. Those are the carbon sp2 there. Those black colored highlighted regions, those are the carbon sp2, which means the rest of the molecule is not flat, the rest of the molecule is not planar, and it does have an optically active carbon. It is optically active because it has a chiral carbon, a carbon bonded to 4 different groups there. You can see here where this is the chiral carbon there, and this one has hydrogen, a CH3, this CH2, CH3, and this alkene group there. You can draw mirror images that are non-superimposible on each other. 2 and 3 are correct. That is option C there. For this next question, 38, so we have an organic compound. It will react with calcium metal to produce a salt. So we're looking at metal plus something to give you a salt. So it has to be an acid. But this salt has an empirical formula, calcium with, well, 1 calcium and then 4. Remember, simplest whole number ratio for all the atoms, no matter how much you want to simplify this, but the calcium one there is really the simplest whole number ratio there. So write a balanced equation. If I try with number 2 first, butane dioic acid. So it's a dioic acid. Carboxylic acid is at the end there, is terminal. So there's 1, 2, 3, and this is the 4th carbon. So it's dioic acid, so there are 2 times carboxylic acid with calcium. Calcium 0 will go to calcium plus 2 to when you form the salt. Calcium 2 plus there, what you get is a dicarboxylate, so O minus like that. Should probably draw a bit better. Let me see if I can draw that a bit better. So there's the dicarboxylate, 1, 2, 3, 4. I need a bit more space actually. I'm gonna move this to the left slightly. So there's the dicarboxylate, and of course I get H2 gas. I get 1 mole of H2 gas because I have 2 carboxylic acid group like that. So this thing here is my product. I just need to check for number 2 first. So what I get is calcium, and then I get 4 carbons. I get 2 hydrogen and 2 hydrogens because these are sp2 carbons. There is no hydrogen there because there's carbon forming 1, 2, 3, and 4 already. Carbon forming 1, 2, 3, and 4 already. So there's just hydrogen from the CH2 and the CH2. C4H4O2. So this is the empirical formula of the salt you're going to get with butane dioic acid. I think let's try number 1. So ethanoic acid. There's ethanoic acid plus calcium. I'm going to get calcium ethanoate. The issue here is this is a -1 charge cation. So to have 2 of them so that you have -1 and -1, -2 cancel out plus 2 like that. So now what you have is C2H3O2, 2 of them, and then calcium, because what you have there is CH3, but this is carbon with no hydrogen, so 2 carbons, 3 hydrogens, 2 oxygens, 2 of them. I'm gonna open up the bracket and expand it. I'm gonna get C4H6 or 4 calcium. I can very clearly see that this one is wrong already. So you can see the H6 there is not 4 as this formula has shown us, CaC4H4O4. 1 is definitely wrong, and therefore if 2 is correct, 1 is wrong. I can only get one answer, which must be 2 and 3. There's option C there. Okay, so in the real exam, you should be able to move on already. But let's just show you 2-methyl propane dioic acid. So I have a dioic acid again. So I have like that, and I have 2-methyl. Of course, instead of drawing out the products and balancing them, what I'm going to do is, I think it's best if I just total out the number of carbon. So this is C4. There are 4 carbon, 1, 2, 3, and 4. There are 1 hydrogen here, 2 and 3, and then 3 more. So there's 6, and there is all 4. 2 there and 2 there. And you can see that these and these are practically structural isomers. Specifically, this one is a straight chain with 4 carbons. This is a branch chain with only 1, 2, and 3. So these are what we call chain isomer. So chain isomer with number 2 there. So chain isomer of number 2. You can see that there are 4 carbons, and there are CH2, and then 2 plus 2 is 4 hydrogen, 5 and 6. And there are 4 oxygens. They both have the same molecular formula, different structural formula, straight chain, branch chain, chain isomer, one of the umbrella that comes under structural isomerism. Okay, since they have the same molecular formula, when they react with that, they're going to give you the same empirical formula as well for this resulting product, no matter how much it would look different. But when you total out the number of carbons, hydrogen, oxygen, calcium for the product for this dioic acid, when they form the salt, it's going to give you the exact same formula, therefore the same empirical formula of the salt that you're going to get there. Question 39, so getting towards the end of this paper now, which one will react with HBr to give the compound R there? So this is an electrophilic addition mechanism of an alkene. So there's the mechanism, but the type of reaction is definitely addition across a carbon-carbon double bond. I'm just going to add HBr. Remember that your HBr could add the H there, add the Br there, or it could be the H there and the Br there. So what happened then is I could just get this thing there, like a single, and could I get a Br there? Yes. Could I get a H there? Yes, and I could get BR and that. So 2 is definitely correct there. So I'm just adding them by removing the double bond essentially. Can I go from OH to BR? Can I do substitution? So that one is nucleophilic substitution. I think I should probably think about my choice of words there. So I should probably do electrophilic addition only for this one. And now last but not least, can I go from number 3 to to R there? Yes, I can, I think. If I add H there and I add Br there, so there's the delta plus and delta minus. So CH2, carbon from 4 bond, 1, 2. So add one more hydrogen there, becomes CH3. Add the Br there, electrophilic addition again. So both of these are electrophilic additions onto the alkene. This going to this is just a nucleophilic substitution there. Okay, so you can definitely do that. Should probably erase that now. Okay, let me just make myself a little bit clear. So these are dotted in the sense that you can proceed with the electrophilic addition mechanism. All three are correct. That's option A there. Question 40, we have this 5-hydroxy pentanoic acid. Pentanoic acid, so 5 carbon carboxylic acid. 1, 2, 3, 4, 5. 2, 3, 4, 5. And you can convert this into cyclic compound here, where this is an ester. 5-hydroxy. So that is got a OH at position 5, but the important one is this carboxylic acid. So you have pentanoic acid as the suffix, and then the alcohol as a hydroxy as the prefix, meaning at the front of the name there. So we have an alcohol, and we also have a carboxylic acid. So in the presence of concentrated sulfuric acid as your catalyst, and of course you reflux this, you're going to form an ester and you will kick out H2O. This is a classic condensation reaction. So you learn condensation polymerization when you form polyester back when you were doing O-level, GCSE or IGCSE level chemistry. So you do produce a water molecule, as this is a condensation reaction here. You're removing the OH from the carboxylic acid, and you're removing the you're removing the OH from the carboxylic acid and removing the H from there, because when you hydrolyze the ester, this is where you hydrolyze, this is the bond that you break. So that thing is the carboxylic acid fragment, and that thing there is the alcohol ROH fragment there. Now this reaction is catalyzed by sulfuric acid, as I mentioned earlier, part of the reacting conditions, and these are the reactants there. Acidified sodium dichromate is used as a reagent. Nope, this is not oxidation. This is a condensation reaction between the carboxylic acid and an alcohol there. So only 2 and 3 are correct. That's option C. We've reached the end of these 40 questions for these June 2015, paper 1-1 for the Cambridge International A-level paper, contents of which are similar to any 16 to 18 years old chemistry curriculum all around the world. Thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel. Follow me at ptet.chemistry on Facebook, Instagram, Twitter, and Telegram. And by far, all the paper tutorials are only accessible for the silver tier members. So if you got friends who are not yet silver tier members, so do consider supporting my channel, supporting my work. It costs about a cup of coffee, and you'll continue to support the channel and my work in producing more quality tutorials for A-level, O-level, IGCSE level, IB level, any sort of 14 to 18 years old chemistry contents all around the world there. Thank you for watching. Thank you for your support. I'll see you in the next tutorial video.